Well, hello class, it's Mr. Cablan here again, and today we are beginning chapter 5, which is basically going to be the foundation of not just for this chapter, but for next chapter as well. And today's lesson is going to be dealing with what's called direct variation. Now, as I'm going to go through the next, not just this chapter, but as well as the next one, I will be making note of a couple formulas that you do need to memorize as we go through the remainder of this course here. So let's get this started here and talk about what it means to take a look at what's called direct variation. So just a very quick summary of what we did in the last chapter. In the last chapter, you learned how to plot points using a Cartesian plane, and you also looked at relationships and describing relationships using uh, the ordered pairs that you did plot on a Cartesian plane, or the axes when you define both the independent and dependent variable. Well, how that applies to this entire chapter is we're going to be looking at more examples that relate to that. And one of the things that we're also going to see in this chapter is how to calculate what was called slope, which I quickly also reintroduced to you in the previous chapter when we're dealing with motion. All right, so let's take a look at exactly what direct variation is. So in this particular chapter, you're going to be seeing a lot of formulas and a lot of equations. And like I said before, I'll be making a note in terms of which ones you do need to memorize for the final exam at the end of the semester here. So what you need to know about direct variation is, again, just going to read this step by step here, is that it occurs when the dependent variable varies by the same factor as the independent variable and begins at the origin. Now, what that is that when you're looking at direct variation, you're looking at a line that starts at the point 0, 0. So if you take a look at the example that I have on the screen over here, you notice we have a line that's going up to the right, and it starts at 0, which I've indicated there with a red dot. Okay, so that all the types of graphs that deal with direct variation always start or pass through the point 0, 0. So that's an important characteristic of equations dealing with direct variation. Now, one of the first formulas that you do need to make a note of over here is this one over here, y equals kx. And what you need to know about this, that this is the general equation of direct variation. So that means that any equations that look like this, okay, are examples of direct variation. Okay, so just make a note of that. Now, what you need to know about this is that this equation here, and you're looking strictly at the letter k, is that the k can be calculated by taking the value of y and then dividing it by x. Now, it's a little bit abstract right now, but once you see numbers over here, you've actually did that at the very beginning of this semester over here. Okay, the k here is what's referred to as the constant variation. Now, that's a very fancy word for what you did actually in the first chapter of the chapter 8 review. It's basically the calculation of rate, and that's exactly what it is. Okay, so what is the difference between constant variation and rate? Well, calculation-wise, absolutely nothing. It's exactly the same thing, just a different way to phrase it. Now, K represents the constant variation or the rate, which can be calculated or will be given to you depending on the context of the question. Now, what you need to know about the y over here, going back to the last chapter, is the y would be the dependent variable, okay, and the x would be the independent variable. And basically, again, when you're calculating that, okay, what you have here is taking the value of y, whatever it may be, and dividing it by the value of x to give you the value for k, which, like I said before, is the value for the rate. All right, so let's take a look at some number examples so it makes things a little bit clearer. So what it says here is the Smith family travels a distance of 120 kilometers in 2 hours. So it tells us here that the lowercase d represents the distance in kilometers, and it varies directly with the time t represented in hours here. So it says you determine the expression relating d to t. Now what this tells us over here is that when we're measuring distance over a period of time, okay, you actually know that to be speed, and that's exactly what we're going to do for this question here is to use that calculation to determine answers for different types of questions we'll be seeing in this example. So it says here, since distance varies directly with time, the way we calculate k, or the constant variation, is taking the distance and dividing it by the time. Okay, so that's going to be the calculation we're going to do for the first step. So it says here, calculate the constant variation k if d equals 120 kilometers, which is the distance of the problem, okay, and the t is 2 hours, which is also the time in the problem. Now, step number one, always start off by writing down the formula or equation that's given to you in this question, which in this case here is k is equal to d over t. Now, all we're going to do here, just like we've been doing, is replacing the letters or the variables with the numbers that's given to us in the question. Now, what you're going to see in this example over here is that I'm also including the units in between the steps over here, okay, just to show you that when you're looking at the final answer for the constant of variation, just like we did for the calculation of rate, okay, you're always going to have two units, okay, one that represents the quantity on top and one that represents the quantity in the bottom. So when we take 120 kilometers and we divide it by 2 hours, what we wind up getting here is an answer of 60 kilometers per hour. So if this sounds relatively familiar, it should, because we actually did this at the very beginning of this course here. So as you can see, the calculation of the constant variation k is exactly the same as a calculation of rate. Okay, so when in doubt, when you're looking at the k, just think of how you calculated rate back at the beginning of this course. Now, what we want to do here is now to take this answer and use it to answer the next following questions. So it's very important that when you're reading word problems that you take a look at the information that's given to you in the previous example here, and then figure out where the numbers need to go. So it says, using the answer from B, which you can see up here, determine how long would it take for the Smith family to travel 300 kilometers. All right, and I'll always start off with the basic formula here. Again, K represents the speed in this example. And as you can see here, we're going to start off with K equals D over T. Now, let's take a moment again just to read the question again, just to make sure we have enough information to solve this problem. So we have three letters. We have K, D, and T. So let's take a look at what we know so far. Okay, you can see the K is going to be the 60. So this 60 would replace the K. And the 300 kilometers is the distance. So that would replace this lowercase d over here. So our next step is going to exactly do that. Put those numbers in for those letters. All right, so now what we have here, 60 equals 300 over t. Now, what you probably want to do for this one, just as a quick reminder, because now we have the fraction, which we dealt with a lot in chapter 4, is we want to find a way to get rid of it using some of the techniques that we saw in chapter 4 when we were solving equations. Now, remember that when you have a fraction, you always want to first get rid of the fraction. Now, if you recall, you get rid of a fraction simply by multiplying both sides by the denominator, which in this case happens to be the letter t. All right, now remember that when we do this, the reason why we did that is if you take a look at the two t's on the right side, they cancel out. So we're left over with 60t is equal to 300. And last but not least here, we're now going to solve for the t by dividing both sides by the coefficient, which in this case here is 60. Again, the reason for that, in a similar fashion as what we did over here, is when we do that, the two 60s on the left cancel out, and then 300 divided by 60 is going to give me 5. Now, keep in mind that this is a word problem, so you do need to state what that 5 represents. So if you take a look at the initial part of the question over here, t here represents the time in hours. So this tells us that in order for this family here to travel 300 kilometers at a speed of 60 kilometers, they will be traveling for 5 hours. Okay, so you can see here how we use information in a question and a formula, put the numbers in, and then solve it using the techniques, algebraic techniques we learned in a previous chapter, and we can come up with the answer from there. All right, let's move along here to the next part over here. So another example we're going to see here. Now we're going to be dealing with rate of pay. Now, before I actually go through, I'm just going to quickly go back over here. In this question, we had to calculate the rate or the constant variation first, because what we had here were two units that helped us determine what we need to do to calculate this value of k. So for this next example, it's very important that you read the question very carefully, because part of the question is going to help us with part of the answer towards the end of this example. So what do we got? So it says here, Jamal works at a music store and he earns $10 per hour. Okay, make a note, I've bolded that for a reason. All right, so it says here, describe the relationship between Jamal's total pay in dollars with respect to the number of hours he works. Now, the best way to look at this is just to think about this logically and using a little bit of common sense. Well, if the more he works, well, the more money he should make. So that's exactly how you describe that. You can use it in your own words if you want. Okay, so it says here Jamal's pay is directly proportional to the number of hours he works. Then you can just reword that by saying, he gets paid depending on how much time he puts into his job. Okay, so again, he gets paid $10 for every hour of work. So this is a verbal of explanation in terms of, how much he's getting paid, okay, and the rate of pay that he's going to be earning for this particular job. All right, so let's take a look at the chart over here. And as you can see, we have on the left side here the number of hours worked. So these will be our values of t. And what we have to do here on the right side here, again, is to figure out how much money he made based on the number of hours that he worked. Okay, so for example, if he didn't work, well, it makes sense that he doesn't make any money. So 10 times 0 gives me 0. All right, so next one over here, he's worked for 1 hour. So if he worked for 1 hour and he earns $10 per hour, he's earned 10. Okay, and moving along here, for 2 hours, he's worked 20. And I think you see the pattern from here, I hope. So we go 10, 20, 30, 40, and last but not least, we have 50. Okay, so as you can see here, as he worked more hours, he was getting more money. Okay, also factor in another way you could have done this is take a look at the first 2 or 3 numbers and notice that they're all going up by 10. So you could have completed it that way simply by looking at the pattern in these numbers here. All right, or you can just calculate the number of hours and multiply it by the amount he makes. All right, let's graph this relationship here. Now, remember when you were given a table of values that looked like this, and this was from previous lesson, is that the left column, okay, will usually or most likely will be the independent variable, and this is no different. So the number of hours worked, okay, that would represent the horizontal axis, which is also known as the x-axis, and same thing with the total pay over here, that will go on the vertical axis. Okay, and so just plot the first point here of 0, 0. So this is going to be the point 0 here, and since it didn't go up 1, it just stays right there. Okay, next one here, at 1 hour, he made $10. So here's 1 hour over here, and we're going to go up to 10. 2 hours is 20. 3 hours is 30. 4 hours is 40, and 5 hours is 50. And if you can see from far away, we can connect those 6 points there with a straight line. Okay, and don't forget to extend. Okay, just again to good habit here of extending lines, because in some cases you might be asked to use the line in order to make a prediction inside using interpolation or outside using extrapolation. Okay, so just again make sure you extend the lines there. All right, let's answer the rest of the questions over here. Okay, using the table as well as the graph. It says, what is the equation which models this relationship? Okay, so for this question over here, we're going to start off with P equals KT. Now, you're probably wondering where in the world these letters come from. Well, another way you could do this, and I'm going to write this way over here, is if you wrote down, for example, y equals kx, which is the general equation for partial variation. Okay, what you have here, if you line up the letters, is the fact that if you sorry, it should be kx. If you line up the letters over here, notice the one letter they have in common here is k. So if you were to line up the p, for example, you'd notice that the p, okay, and the y would be the same. Okay, obviously the k and the k are the same, and the t and the x would also be the same. So when you're looking at this is going to be our equation which models this relationship using these variables or letters. Now, the next part over here is we want to figure out where in the world the numbers go based on the initial word problem. Now, one thing you need to know about equations is the fact that the only thing that you will be replacing or substituting for the equation of direct variation is this letter K. Now, I want you just to take a quick glance at the entire question for a moment, and I want you to see if you can find what the value for K might be. Now, just remember K, which is a constant of variation, is also known as the rate. Now, if you take a look at this question here, I hope you notice that the best way to find out where rate is in the question, if it's given to you, is if you're given something per something else. So if you read the question again, you notice that there's a $10 per hour over here. okay, which is in the question. Okay, so that $10 per hour would be the rate of pay of $10. And that's important here because guess what? That's what replaces the K. So you can see here that this equation, P equals 10T, is the equation that models this table here as well as the graph from the previous slide. Now, question D, it says use the equation in C, rewriting it here, to determine how much Jamal would earn if he worked 9 hours. So all we're going to do here is we're going to take this 9 and then substitute it in for the T. Now remember, when you substitute a number in for a variable, all you need to do is to take the number and then put brackets around it, and then from there that will replace the variable, which in this case here is the letter T. Okay, and then last but not least, 10 times 9, that's going to give you 90. Now remember that this is a word problem, so you do need to state what this 90 is. And since it tells us here that it's the pay in dollars, this tells us that if he worked 9 hours, then he would get paid $90. And that pretty much summarizes that question there. All right, that wraps up lesson 5.1. Okay, and I will see you in the next lesson.